Okay, let's look at the Orthohack verifier. You can see I've run the post processor and captured it to orthohack.h as required. You do probably just want to run it first without capturing it to make sure there's no overflows. Otherwise, you'll get tons of build errors when you try to make the verifier. So now let's run the verifier. So if you're dealing with an orthonormal transform, and only if you're dealing with an orthonormal transform, as most engineering useful transforms are, you're going to get meaningful error information here. So what does this mean? So if we look at particularly the floating point values, we've gone through the entire original orthobasis database, and we've done transforms on every single one of those orthobasis vectors. And so the assumption is that because we're using an orthonormal transform, that every time we do one of those transforms, we're going to get a coefficient of 1 in the location corresponding to the given orthobasis vector, and all of the other coefficients are going to be 0. So the deviation between that assumption and the empirical reality is the error, right? So the worst error we ever observed, either the difference from 1 to 1 point something, or 0 to 0 point something, or negative 0 point something, was 2 times 10 to the minus 16th. And the mean squared error was actually much less. And then we do the same thing for fixed point and custom fixed point. Now, I might add, obviously, if you're doing a transform on some different kind of data set other than the orthobasis vectors, then you might have slightly different error metrics. But this is nonetheless an informative test. And you can see, of course, that as we go to fixed point, our error kind of explodes, and it grows a bit more when we go to custom fixed point. But even so, 4 times 10 to the minus 7th is very useful for a lot of practical signal processing purposes, and custom fixed point is way faster than anything else here. So that all looks quite good. And then down here, we see these minimum and maximum coefficients. So let me explain a little bit how this is computed. So we assume, first of all, that in fixed point transforms, the smallest input, the most negative input, is -1, and the maximum possible input, this is sample point input, is 1 minus some epsilon, which is one incremental unit, right? So it's the integer range from 8,000 to 7 FFF if you like, or the 32-bit and 64-bit equivalents of that. So in fixed point, for instance, it would be FFFF, 8 Fs. This is only 7 Fs, but it would be 8 Fs, and then a bunch of zeros would be -1, and then in the positive direction, it would be a bunch of zeros, a 1, and then a bunch of zeros, -1. So it would actually be a bunch of zeros here and a bunch of Fs down here would be the maximum, the most positive sample input that we could have. And based on that assumption, we go through and iteratively figure out over all of the orthobasis vectors what is the maximum possible resonance that we could get, which gives us in turn the minimum and maximum possible coefficient. I'm 99% sure that this is actually a valid statistical approach, but if anybody wants to say that this is wrong and the range is actually larger, let me know, and we can change the code. But anyhow, that does give you good coverage for overflows. And then the floating point min and max, of course, floating point being what it is, these are approximations, but this is really just more of a sanity check on the integer exact values which are above. So you can see actually -6 does look like F9, and 6 looks like 0.6, because this part is the fraction here, and the 0.6 is the integer. So those do sync up pretty well. I think that the analysis seems to have been done correctly. And so if I look at this, I notice that there's 4 bits that are equal to the sign bit, one of which is a sign bit, and then there are 3 regular integer bits that are equal to the sign bit. So this tells me that I've probably got 3 more bits I can use for fraction precision. So let's go ahead and try to crank up the custom precision. Let's go to 27 bits. Okay, and now that we've done that, we're going to have to rebuild and rerun the post processor because the format of the custom underscore list is going to change in orthohack.h. And we can rebuild the verifier, and we'll rerun that. Uh-oh, custom sum overflow. So it turns out that one of the intermediate values is large enough in the transform that we overflow when we're trying to sum 2 custom fixed point numbers together, and our formal verification process caught that. So whenever we do a sum, or for that matter, a difference, or a product, or a negation, we're checking for overflow. And so what we're going to have to do is we're going to have to go back down to, in this case, 24 fraction bits. By the way, if you don't care about custom floating point or overflows and they're just getting in your way and you can't get the post processor to finish or you can't get the verifier to finish successfully, you can just turn all that off. And the way that you do that is in config.h. Just simply delete this line here about overflow check. Okay? So that's it. In the next video, we're going to talk about the literalizer.